Okay, we're picking up where we left off last time with the cathode ray tube. It led to the discovery of electrons. And after the discovery of electrons, the scientist by the name of J.J. Thomson was pursuing more information about electrons, specifically their size and their mass. And that's where we're going to pick up. This is J.J. Thomson. By the way, this is your early 1900s. We're talking 1905, 1906, sometime around then. So J.J. Thomson's research determined an electron's size and mass. And this symbol right here I've highlighted is size and mass. So he realized that electrons are smaller than a hydrogen atom. Now, you guys are going to get more chemistry than you've ever gotten in your entire life combined. You may have talked a little bit here, a little bit there. You might have mentioned density here, hydrogen there, but not to the degree you will in this class. So I don't expect you to know everything, but it'd be nice if any of you could participate if you know it. Do any of you know what element, and of all these, has the smallest sized atom? Like it is the smallest element in the universe. Varun? Hydrogen is it. That's why I said hydrogen, not carbon or oxygen or uranium. Hydrogen, the reason why that's so significant is it is the smallest atom in the universe. It's the smallest atom there is. In fact, what was it? The majority of the universe is made of hydrogen and helium. Those are the two smallest elements. So here's the ramifications of this statement. You guys might not get it so clearly. Electrons are smaller than a hydrogen atom. That's because there's actually something smaller than hydrogen. That's the big deal with that statement. There's something smaller than an atom. You know, carbon is bigger than hydrogen. That's easy. But there was once thought there's nothing smaller than an atom. And hydrogen is the smallest atom. Well, J.J. Thomson realized electrons are smaller than what they thought was the smallest thing. And so here's the big ramification. There are particles smaller than atoms. And what are those particles called? Well, electrons are one of them, but protons, neutrons, and electrons, what are they all considered? Subatomic particles is right. So here's something else to consider. Last week, I told you about John Dalton, who proved Democritus was wrong, or sorry, right? But there were a few things John Dalton did not get correct, and this was one of them. John Dalton was incorrect with this. He stated atoms are indivisible. That means they cannot be broken down any smaller. Atoms is as low as they can go. That was an incorrect claim. And because of J.J. Thomson's work, he earned the Nobel Prize in 1906. Which is a little more than 100 years ago. All right, let's go forward a few years to the 1910s, 1910 through 1919. We have a new dead guy. I don't think I have his picture. Robert Millikan. If you're watching this YouTube video, it is because we are watching it the day before a hurricane, and everyone's phones are now going off because there is a hurricane warning for Hillsborough County. That's all your phones combined. All right, let's just wait it out. Hey, your phone just told you there's a hurricane. That was fun. All right. My students in 20 years are going to look back at this and go, dude. All right, here we go. And by the way, it is August, what, 28th, 2023. I once did a YouTube video a few days for the Bucs Super Bowl. I was like, okay, guys, hopefully the Bucs going to win. Look back at that. Why were we worried? We won by 20 some points. All right, back to this. Robert Millikan determined the charge of an electron by performing the oil drop experiment. Jeez. Here we go again. Well, the good news is we are not in the cone right now, but one little wobble, and it can go towards us. So let's keep an eye on it. Okay, we get it. Hold on. Okay. All right. So how did he prove this? With doing this thing called the oil drop experiment. I'm not going to get into the particulars actually with this, but what he did show, because you don't need to know all that, he realized that a single electron carries a charge of -1. And in chemistry, we actually write the number first and then the positive or negative symbol. As far as the mass of an electron, it is 1,840th the mass of a hydrogen atom. That is 0.0005. So it's 50,000 times less than a hydrogen atom. Very tiny. In fact, of the 3 subatomic particles, electrons are the smallest of the 3. Okay, so that's pretty much covers it with electrons, but then we got to talk about the other subatomic particles, which I'm sure you've heard of before. So are there other subatomic particles? Well, we know there are. Okay. But how did they find them? It is now known that electrons exist. All that was from the 11 a.m. advisory, guys. That's why I went off at that time. Electrons have a negative charge, which is going to be really important. So here's the problem. This podium is made of atoms. My hand is ultimately made of atoms. The air, there's oxygen and carbon dioxide in our air. That's made of atoms. If they only have electrons, why are we not being electrocuted by it? I'm looking at you with your elbows on the table. Why are you not being electrocuted? I see you holding your pencil. Why are you not being electrocuted by it? If the only thing in these atoms is electrons, shouldn't these electrons be zapping us every time we touch something? Well, they realize we don't get zapped. I touch my podium. I don't get shocked. I touch my hand. I don't get shocked. You touch your table. You touch your pencil. You're not being shocked. Something is offsetting the charge of the electrons. And what could offset electrons which have a negative charge? Something with a positive charge. There's a reason why we do not get electrocuted when we put on our shoes, when we touch our tables, when we pick our nose, when we drive our cars, because what we touch is neutral. Well, they realized this. They thought, all right, we know electrons are out there. We know those are in atoms. What's canceling out the negative charge? And so here's the question. Why or how is matter neutral? What is in an atom that is canceling out the negative charge? So here's an early idea. Early ideas aren't always right. Remember the early idea the earth is flat or the earth is the center of the universe? Those are early ideas. They can be proven wrong. J.J. Thomson had the plum pudding model. Here's what that is. You have an atom. You have electrons. And then all of this space in here that I'm going to highlight with yellow, all this empty void in between the electrons is supposed to be a positively charged space. Now, as I said earlier, you guys are taking like real deal, legit honors chem for the first time in your life, but I'm sure you've heard of protons before. There's no protons in this image. This was an early idea. They thought that electrons exist in a void within an atom that is a positively charged space, and that's how they cancel each other out. So what I put in my notes, which I'll add to yours, is nice try, but no. Obviously, this is not how atoms look. This is not correct. So that gets us to something in an atom called the nucleus. And we are now in 1911. Let me get one of my other dead guys' pictures down here. Come on, Ernest. Let's go. Okay, this is Ernest Rutherford. Remember that last name, Rutherford. He did an experiment where he fired alpha particles at a gold sheet. Now, here is what his expectation was. This is a gold atom. Gold sheets are obviously made up of gold atoms, right? What are these randomly scattered dots that are all throughout an atom at the time that they thought this was real? These are electrons. Okay. And then he would fire his alpha particles, and he thought they would do this. These are alpha particles. He thought if J.J. Thomson is right, these alpha particles will just go right through. You got to realize, if you haven't already realized in your life, there can be a difference between expectation and reality. Aiden, you might have the expectation you're gonna walk up to a girl, say, hey, you, me, prom, be there. That's your expectation. Then you walk up and say, hey, my name is Aiden. Will you go to the prom with me? She goes, oh my God, really? There's reality. Two totally different things. You play football, right, Aiden? What position? Let's say that your expectation is 20 touchdowns in a game. All right, well, in reality, 3 touchdowns, 1 pick. You got to know that this was the expectation. Let me show you what actually happened. So here is the observed. In science, we don't say reality, we say observed. He shot his alpha particles at this, and deflection. Some went through. Some got bounced back right at him. Some got deflected. This is not what he expected. He shot his alpha particles at the atoms, and they were deflected in all directions. Some went through, some didn't. What do you think the beams that were deflected ran into? Something very, 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 very dense, dead center in these atoms. And so he tried to explain, Rutherford attempted to explain the deflections. What is deflecting these beams? I thought J.J. Thomson was right. The atom is made up of randomly scattered electrons, and they're in a big positive void. Wrong. Remember, I wrote that. Nice try, but wrong. The beams hit something. As Alex said, they hit something called a nucleus. So Rutherford determined J.J. Thomson's plum pudding model was incorrect. He also concluded the majority of an atom's mass is located in a positively charged dense region in the center, and we call that the nucleus. And so this explained a lot. This is why we don't get electrocuted by everything that we touch. We don't get electrocuted by our gum when we chew it. We don't get electrocuted by our shoes when we put them on, because everything has a neutral charge. He realized that the nucleus is positive. The electrons are negative. They cancel each other out. So here's the big one. As I just said, the positive nucleus and the negative electrons balance into a neutral charge. So guys, we've done electrons now. We've done the nucleus, but as some of you may know, the nucleus is made of something. And that's where we're going to start to wrap things up. This is our last big topic here. Protons and neutrons. By 1920, nearly 100 years ago, 123, Rutherford determined the nucleus contained positively charged particles called, what were they called, fourth period? Protons. So if an electron has a -1 charge, what must a proton be in order to neutralize it? No. Well, let me go with that. If a electron was -1 and a proton was neutral, what is that equal to? What is -1 plus 0? That's still -1. So what must the protons be to neutralize the electrons? +1. A proton results in a +1 charge. They cancel out the electrons. So here's the thing now, guys. You said this correctly earlier. What is attracted to a negative charge? A positive charge. What's attracted to a positive charge? A negative charge. So I have a question for you. Let's say here's the nucleus. Here's the nucleus. And that's a proton. Here's an electron. Based on this knowledge now that one is positive, one is negative, could you conclude that they would be attracted to each other? Positive attracted to negative? Yes. So why don't they go to each other? If my phone is a proton and my clicker here is an electron, you would think they want to be together. Positive attracts negative. But here's what they realized. Protons stay put. Electrons stay out here. What is keeping them separate? That was the next and final big question. Here's what they realized. There is something in the nucleus keeping the protons still. I want you to imagine this. Turn off for a second. Just look at it. You want no, turn around. Go, flip your chair. Okay. You want to destroy this kid. He stole your French fries and you're 5 years old. Yeah, him. At your birthday party, you want to destroy him. Now, what do people tend to do when someone wants to fight someone else? They hold him back. Now, you want to go get him. All right, you want to knock him out. I'm holding you back. What am I supposed to do? I'm in the nucleus. I'm keeping this proton from going over to that electron. Without me, he's going to be right over there. Proton, electron, together. I'm holding him back. So what's that third subatomic particle that must be in the nucleus that's holding the proton back, keeping it in the nucleus? What's the one we haven't done yet? Neutron. A neutron. You guys are friends, right? Yeah, don't destroy each other. So, only in Madden and Smash Brothers and on the football field can you. Isn't that crazy how, like, I've never known something that can make friends enemies other than like Madden or something. Just all the talking and oof. I think I lost some friends back in the day. Rutherford's colleague, James Chadwick, discovered a third particle, also in the nucleus. And this was the neutron. So I'm going to try to skip you guys ahead a few lessons, and I really hope this makes sense for you. It took me, when I was in your position, a long time to figure out. So watch this. proton, electron. Negative, positive. The force that attracts these two, positive charge to negative charge, is called electrostatic attraction. And you guys are honor students, so I need you to be thinking here. What do you suppose the term is where you have positive and positive, negative and negative, and they actually hate each other? Positive hates positive, negative hates negative. If electrostatic attraction is where positive goes to negative, what do you think the term is where positive, you play with a magnet before, you try to get the two sides that have the same charge to bounce off each other and they just won't go together. What is that known as?
Attraction.
Not detraction, but it does mean the same thing.
Like repulsion.
Repulsion. It's called electrostatic repulsion. That's something I just wanted to plant in your brains. Now, here's what I'm getting at. There must be a force that is stronger than this. His drive to want to destroy his friend is strong. But if I'm holding him back, I must be stronger. And that's what the neutrons provide. So over here is a neutron. And these two have a nuclear force. And that nuclear force is stronger. That dog is tied up to a tree and he wants to eat your guts out, but he's tied down to that chain on the tree. That chain is stronger than the dog. That's like the nuclear force. The neutrons keep the protons in the nucleus. That is why I want you to write. The neutrons keep the protons in the nucleus. All right, we're running out of time here. So the last thing I want to do is I want to make a data table to give you some pieces of info. I want to try to finish this for the bell. The first column is going to be particle. Electron, proton, neutron. The symbol, E negative, P positive, N. And what I do, I put in 0. That's a 0. Guys, give me 10 seconds. I'll get you out of here. Location. Nucleus. Nucleus. Oh, wait. Electron's not nucleus. Orbit. Nucleus. Nucleus. Charge. -1, +1, 0. And then mass, and that'll be it for today. 0.00005 AMU, 1 AMU, 1 AMU. Okay. Get all that and you're free to go. You got all that, right? I saw you put your stuff up.
Oh,
All right. If we don't get too much damage over the next few days, I'll see you on Thursday.